Hello, my name is Justin Kreiselman, and this is our game, Machine Learning Arena. This project was developed with Jordan Cattelona, Grant Ferguson, and Kyle Corry. The project was supervised by Professor Smith and Professor Whitehill. In our game, you will play as a coach as they try to train a new entrant named Roboxer to compete in the Machine Learning Arena. The player will teach Roboxer how to punch and dodge so it can compete on its own against other robot boxers. Our game has two main gameplay phases, training and fighting. In the training phase shown in the left screenshot, the player will fight against a simple AI robot to show Roboxer how to dodge and punch. You will train Roboxer for a minute at a time. Afterwards, you will be given the opportunity to see it perform what it has learned and be given the opportunity to train it some more or send it into the main event. The second gameplay phase is the main fight between Roboxer and its opponent. The player will watch the Roboxer compete and either win or lose. Here's an example of our game in action. First, you will start with the tutorial section, teaching you how to punch and how to dodge. Here we are describing to the player that consistency is key in order to have Roboxer learn the best. Here we show the resource meters that are available to the player. The top one is the copy meter. This gives a percentage of how much your actions are matching to Roboxer's actions. The reward meter shows how much your actions are having reward or influencing the Roboxer. Train of thought is what Roboxer is currently thinking. It takes a while for the train of thought to start up, but once it starts to actually recognize some patterns, it will appear. Training is split up into three separate phases. For the first 15 seconds, you will focus mostly on dodging. In the second 15 seconds, you will focus on punching, and consist with combos such as left and right, or right, left, right. When there's 30 seconds left in the training phase, you will combine the dodges and the punches together. When the training time is up, Roboxer will take the stage and show off what it learned. Afterwards, you will be given the opportunity to train Roboxer some more, or to send it into the final match. Let's see how our Roboxer does. During this portion of the game, you will be watching Roboxer compete. You do not have any direct control over Roboxer. For our project, we use machine learning to train our AI. With machine learning, there are multiple techniques that one could use. In supervised learning, the agent will derive a function to map the given inputs to the corresponding outputs. Then once presented with new input, the agent can infer how to act from the connections taught to it. In reinforcement learning, an agent will learn how to take actions to maximize a reward. A reward is some value that can be mathematically calculated in a way determined by the developer. In a neural network, the agent uses a series of connected nodes that can trigger depending on if the activation method is achieved, resulting in a certain output. We use a combination of these techniques for our game. For our project, we use the ML Agents Toolkit for Unity. The toolkit provides a way to train in-game agents using reinforcement or imitation learning, as well as using a pre-trained model. The core of ML agents is the brain object, which can either be a player brain, heuristic brain, or a learning brain. The brain acts as a controller for an agent object. which is the base class that needs to be extended by the game agents. Agents collect observations about their environment and use the brain to determine the proper actions to perform. Within ML agents, we use behavioral cloning. Behavioral cloning is an imitation learning algorithm that can be used to copy the behavior of an agent in real time. Behavioral cloning records input-output pairs from one agent, which may be human-controlled, and conducts supervised learning through mini-batch gradient descents on a neural network. This technique worked the best for us since we were able to train the model as the game was played and did not need a previous play trace to train on. We've made many changes throughout development. On the left, this was our original UI prototype that we created for the game. This was our original idea of what the game would have looked like and the training tools the player would have to train their fighters. On the right is our current build. Some of the changes include overhauling the art assets and UI. Instead of having the coach and Roboxer train at the same time, we now have the coach fight first and have Roboxer watch from the sidelines, before swapping in to show what it had learned. One of the biggest challenges we've faced is communicating how the training is going to the player. We decided to approach this problem using 3 UI elements: the copy meter, the reward meter, and the train of thought. The copy meter shows how much Roboxer has learned from the player. This was designed to allow the player to quickly glance over and see a general result while maintaining focus on the fight. The reward meter shows how much reward is given to Roboxer from the player's inputted actions. This is represented as a yellow meter that increases in length when the player inputs an action that gives a high reward value. The train of thought shows the actions that Roboxer is thinking to perform. This is represented by 4 icons moving up on the screen. The 4 icons are the icons used for the controls and represent the left and right variants for punching and dodging. These icons were designed to allow the player to quickly recognize what type of action their agent is currently trying to use while not fully diverting their attention away from the training in the center of the screen. This is what the placement of the UI elements look like in game. We wanted to make sure that these elements were available for the player to quickly glance over and get the information without losing focus on the fight in the center of the screen. At AlphaFest, we noticed that all of our playtesters were having trouble getting Roboxer to both dodge and punch. From our observations, the players did not provide consistent enough input for an ML model to properly learn a policy. For example, we observed that many players punched the training dummy while they were throwing punches and only occasionally dodged. This behavior seemed to cause Roboxer to only learn punches, and the opposite if players dodged too much. And our playtesters did not think it learned from them very much. Many of our playtesters also stated that they thought Roboxer should have dodged at least a few times, even though they only showed it a handful of successful dodges. To address this, we decided to filter the player's input before training on the data. The following scenarios are filtered out: throwing a punch while the opponent is punching, dodging while the opponent is doing nothing or dodging, and hitting a key while performing an action. The player is still able to perform the filtered moves during training, but the machine learning system will not use them for training data. After conducting several more playtests with the filter in place, we determined that the players enjoyed their experience and felt that Roboxer learned from them. By doing this, we discovered that a balance needs to be achieved between having a pure machine learning game, which trains off of anything the player does, and a fun game that allows for learning characters but is a bit scripted. For our concluding experiment, we tasked players to identify the difference between a random agent and a learning agent. This would give us insight into whether people could actually tell that Roboxer was learning from them rather than just coincidentally performing similar moves. We disabled the training progress indicators prior to having our participants play the game, so that we could just focus their attention on Roboxer's behavior. We then chose an AI random or learning at random for them to play with. After completing the game, we had them play a game with the other AI and then asked them to identify which was random and which was learning from them. In total, we had 27 participants for our concluding experiment. 23 out of 27 participants correctly identified the learning agent from the qualitative elaboration from players, we learned that they were able to tell which one is a learned agent because they recognized some of its moves as their own. For those that incorrectly identified the random agent as a machine learning agent, different reasons were given. One player felt that the rapid twitchy actions of the random agent were closer to how they played. Another player reported that the actions of the trained agent were too good, and so the random roboxer must have been the one that learned from them. The goal of this project was to create an experience for players in which they could train a boxer how to fight and defeat a simple AI boss. Machine learning can be used to learn unique behaviors from each player and customize a gameplay experience to match how they play. Our project demonstrates that a game centered on machine learning can be challenging, yet enjoyable experience for players. We were also faced with several challenges in creating a machine learning-based game, such as communicating machine learning progress to players and obtaining good training data during gameplay. From our project, we learned that the imitation learning can provide players with a unique gameplay experience. We experimented with multiple imitation learning algorithms and found the best results with behavioral cloning. We also learned that conveying machine learning information to users is vital, and as a result, we created multiple UI elements related to training progress. Overall, this project explored building a game focused on machine learning and how to convey that to players. Machine learning is relatively new to video games, and there were plenty of unexplored areas that have the potential to impact the future of how we interact with video games. We hope to see more video games that utilize machine learning in innovative and entertaining ways.